Hey everyone, let's take a look at estimating with finite sums again, this time estimating area using the trapezoidal approximation method. So instead of squeezing rectangles under the curve this time, let's squeeze some trapezoids under the curve this time. Now trapezoids are interesting because they kind of have that slanted distance, right? And that might make our area a little bit closer to the actual area under the curve. Now trapezoids have a couple of different dimensions we need to be concerned with. We have what's known as the height of the trapezoid, and then we have these lines right here, which are known as the bases. If you ever have a hard time determining the difference between the height and the base of a trapezoid, the bases are always parallel to one another. So the area of a trapezoid formula is equal to 1/2 times the height times the sum of the bases. So if you think about each trapezoid in this, there are kind of like 4 blue trapezoids. We'll call them trapezoid 1, 2, 3, and 4. You ask yourself what these trapezoids have in common. So if I calculated the area of each of them, they would each have the 1/2 in common, and they would each have the same height. Just like the rectangles, we have to make them equal height, okay? So that means that each of these trapezoids has a 1/2 h in common. Well, that means that all you have to do is factor out the 1/2 h and then add up all the bases. So this little distance right here we'll know as B1, and this is we'll call B2, okay? So the area of trapezoid 1 would just be 1/2 times the height and then times the sum of the bases B1 and B2. But trapezoid 2, those bases are B2 and B3. Trapezoid 3 uses B3 and B4. Trapezoid 4 uses B4 and B5. So the area formula is starting to look a little something like this. 1/2 times the height times B1 plus B2 plus B2 plus B3 plus B3 plus B4, and so on and so forth until you get to B sub n minus 1, which is the second to last one, and B sub n, which is the last one. Well, interestingly enough, every single base in this problem that's on the inside of the problem is used twice. Let's go back and look just real quick. Notice that this base right here, because it's on the inside, this base right here, and this base right here, they're all used in 2 trapezoids. That means that that base is actually being doubled. The only bases that are not being doubled are base 5, the last base, and then base 1, the very first base. They're only used in one single trapezoid. So therefore, we can kind of summarize the trapezoidal rule to be the area is equal to 1/2 times the height times B1, only used once, plus 2 times all the other bases in the inside, plus the last base, B sub n, used only once. Whatever that base is, could be base 5, base 4, base 3, depends on the number of trapezoids that you squeeze underneath your curve. This is the trapezoidal rule. Let's see it in action. Oh, that's right, we should talk a little bit about this. It says, if y is concave up, the trapezoidal rule will be an overestimate, and if it's concave down, the trapezoidal rule will be an underestimate. We can go back to our picture and verify this is true. Let's look right here. This curve is concave down. I'll switch colors, blue. This curve is concave down from here to here, right? This shape is concave down. Notice that the trapezoidal rule is missing some area here. It's missing this area. So that means it's an underestimate. So concave down, underestimate. Concave up, now we have a concave up curve. I'll get rid of this. Concave up from here to here. And notice this time when the curve is concave up, the trapezoid overshoots it, and it uses too much area. And so therefore, it's an overestimate when it's concave up. So we're going back down. That's my summary, my shack tips for this particular one. Let's try an example now. Okay, so this one says, use the trapezoidal rule to approximate the area under the curve of y equals x cubed from 0 to 2 using 4 trapezoids. So the first thing we could do is understand that in this example, we're squeezing 4 trapezoids between 0 to 2. So that means we have 2 spaces to squeeze 4 trapezoids. They'll each have a height of 1/2. So this is my height, or sometimes we refer to this as delta x, of my trapezoids. All right, let's see if I can sketch a quick picture. So let's draw a picture. This is x cubed, and this is 2, and this is 1, and this is 3 halves, and this is 1/2. So my trapezoids will each kind of live in this region right here. And let's go ahead and draw the first trapezoid. So the first trapezoid is going to be between here and here. It's a little tough to draw it, but it would look a little something like this. Trapezoid 2 is going to be between here and here. Again, a little tough to draw, but it's going to be like here to here. So trapezoid 1, trapezoid 2, trapezoid 3, and the last trapezoid, trapezoid 4, which will be a little easier to draw. A little easier to draw trapezoid 4. So we know that in the trapezoidal rule, it's going to be the area, the approximate area is equal to 1/2 times the height. Well, I know the height in this particular example is 1/2 as well, times the first base of the problem is not doubled. Now, I know the first base of the problem is just the value of f of 0, which is just the 0 in this case because the curve is x cubed, plus, now I'm going to double all the remaining bases. So the next base is going to be f of 1/2, followed by f of 1, followed by f of 3/2. Those three bases at 1/2, 1, and 3/2, they're used twice in two different trapezoids. Those are the only ones though, so I'm going to stop doubling, and I'm going to add f of 2, which is my very last base used only once. If I calculate this, it actually comes out to 1/4 times. Each one of these values is 0 plus 2 times. This first value is 1/8, the second value is 1, third value is 27/8, and the fourth value is just 2 cubed, which is 8. And so we're going to get an answer of approximately 4 1/4, and we'll call it units squared. So the trapezoidal rule gives us an approximate area of 4 1/4 units squared. One interesting thing to note, trapezoidal approximation is actually the average of L and R RAM. Very interesting, but MRAM is not the average of L and R RAM. If you want to prove it to yourself, you can go back to the previous video we did with rectangles and average all the values of L, R, and M, or L and R rather, and see if they come out to MRAM. And it's actually not. It's actually equal to the trapezoidal approximation. Very cool.